Hello, everyone. My name is Jesse Bischof. I'm a senior scientist here with SilcoTek Corporation. And welcome to the first episode of hopefully many video podcast series that we're calling SilcoTalk. Essentially, we're looking for a way to get more information out there about SilcoTek and our coatings. We're going to do that via webinars, potentially interviews with both scientists all around the world, as well as with folks here at SilcoTek Corporation and tell us a little bit about what they do and how things work here. We're also going to do what this particular episode is looking at, and that is reviewing some of the cool things that are going on in the literature using SilcoTek's coatings. You'll probably be seeing quite a good bit amount of me as well as my other R&D members, Min Yuan and David Smith. You'll likely see some of our marketing crew, our sales crew, as well as just a variety of people around SilcoTek Corporation. So with that, let's go ahead and get into this month's presentation. So like I said, there's a lot of really neat, interesting, cutting-edge research that's going on utilizing SilcoTek's coatings in a variety of different applications. And what we're going to look at is a couple of papers that were published in January of 2025, where they utilized one of our coatings in a kind of interesting, neat way for an interesting purpose. So with that, we'll go ahead and get started. So the first paper that we want to look at is a paper that was published in the Journal of CO2 Utilization. It was a group out of Sweden and the Netherlands, both collaborated on this particular paper. And they were looking at carbon dioxide and it being produced from various biogas plants and being able to capture that carbon dioxide and reutilize it for some other kind of application. So first of all, what is a biogas plant? Well, a biogas plant is pretty simple in its design. You take waste of some sort, whether that be from livestock, such as cow manure or a variety of other different wastes, as well as silage from corn, wheat, other plants that you might grow, things that really the farmer or the municipality doesn't have any ability to really use or do anything with. You throw them all into an airtight bioreactor. You add microbes that essentially munch on any of the hydrocarbons that might be there. And from that reaction, you get a large amount of methane, which you can then collect and use. You can compress it as natural gas substitute. I'm wearing my Penn State University College of Everly Science fleece today, because if anybody has been on Penn State's campus and you've heard the buses that go all around Center County here, they are all powered by compressed natural gas, and some of it probably does come from various biogas plants around the area. The other thing that these biogas plants will produce is carbon dioxide. And so depending on the biogas plant, sometimes that carbon dioxide is collected and reused for other applications. Sometimes it's just emitted as an off gas. Now, if it is collected and used for a variety of other applications, one thing that you have to consider, both the methane and the carbon dioxide, is the purity of those particular things. And so you can see in this bioreactor, anybody that's done any sort of bioreactions know that you're not going to get just one pure product out, or even in a non-bioreactor in your chemical synthesis, you're not going to get a pure product out. You're going to get trace amounts of impurities that you want to try to mitigate or take care of in some way. And in a lot of these bioreactors for the biogas plants, they'll produce things like hydrogen sulfide, a variety of siloxanes, ammonia is a big one as well. And then there's too many really to list here, but these are some of the big ones that are rightfully concerning to anybody that is going to be collecting the methane or carbon dioxide for usage. Now, putting CO2 to use, this is a really nice paper from the International Energy Agency. They were looking at basically how can we collect more CO2 and use it more rather than just emitting it out into the atmosphere. We all know the issues with emitting carbon dioxide out into the atmosphere as a greenhouse gas and climate change going on. However, one thing that you can do is collect the CO2 and then put it into a variety of different areas, such as fuels, chemicals, building materials. Unfortunately, currently, only about 1% of CO2 that is produced at some sort of manufacturing process is actually captured and reused. And of that 1% that's captured and reused, you can see on the right-hand side here, it's a little breakdown of where it's used. You can see well over half of it is used in urea production. So that's used as a fertilizer and basically goes back to the farms where the biogas may have been made. And then it is used for fertilizer. There's also EOR, that's enhanced oil recovery, so that you can use CO2 as a means of collecting more oil from various reservoirs. And then very small amounts go into food and beverage, as well as fabrication metal, and 4% goes into a variety of other applications. Now, this particular paper where they were looking at biogas plants and the collection of CO2 and looking at the purity of the collection of CO2, they were really focused on food and beverage, as it's an emerging market to use as a waste product from biogas plants. Now, why do you need purity? Well, in 1999, there was a really interesting event that occurred. Essentially, a Coca-Cola plant in Belgium had tainted carbon dioxide. Now, that carbon dioxide is used to essentially just carbonate their beverages. You take flat, sugar water, you carbonate it with carbon dioxide, and that's what gives us all the bubbly feeling that you get whenever you drink it. However, unbeknownst to the Coca-Cola plant, they did have trace amounts of hydrogen sulfide in their carbon dioxide source. Some of the papers I read said that it was well below 1 ppm. However, hydrogen sulfide is a really, really important thing to keep out of food and beverage, because our noses have become so adept at being able to detect hydrogen sulfide that as soon as people were opening these Coca-Colas that were produced at this site with the tainted carbon dioxide, they can immediately smell it. Interestingly enough, and I'll let you go ahead and read any that you want to read about this. A lot of the medical experts aren't quite sure if a lot of the people that fell sick due to consumption of this were actually sick from the hydrogen sulfide, or if it was some sort of psychosomatic effect where they smelled the Coca-Cola being a little bit off and something in their head made them feel sick as a result of that. But either way, it was multi-million-dollar settlements with Coca-Cola and people in the area that had consumed this particular carbonated beverage from tainted carbon dioxide. So in the paper, they're looking at collecting carbon dioxide and then sending it for analysis to make sure that the purity is where they want it to be. And they looked at essentially 3 different methods of collecting the carbon dioxide. First, they looked at sampling bags. They looked at sample cylinders. Now, the sample cylinders that they used were actually sample cylinders that are not coated here at SilcoTek Corporation. Those are some pictures of our coated sample cylinders, but the ones that they used were not performed here at SilcoTek. And then finally, sorbent tubes from our friends at Marks International. Now, essentially what a sorbent tube is, it's a stainless steel tube that is often coated by us here with our SilcoNert coating. And then it is packed with a sorbent material. So that sorbent material will collect any of the gases that flow through there. And then what you can do is you can cap those, send them out for analysis. And the reason why they're called thermal desorption tubes is because you can heat them up, desorb the particular compounds you're interested in looking at, and you can then analyze them usually via GCMS. So the results that they saw from the thermal desorption tubes that they tested, you can see here the TTA, CG5, the odor/sulfur, and the TTA. Those are all the different sorbent materials that they packed into the coated stainless steel tubes. And you can see how some of them worked well for some of the impurities that they looked at. Others did not work as well. And you can see amongst all three here, the TTA was the one that worked the best, although they did see some methanol and dimethyl sulfide breakthrough. And so the breakthrough just means that it didn't fully get sorbed on the tube. They had a couple of tubes in parallel, and some of the methanol and dimethyl sulfide actually got sorbed on the secondary tube rather than on the first primary tube. Now, interestingly enough, the one thing with methanol was the authors had mentioned that really none of the sampling methods were able to look at methanol and be able to really quantify that in a good way. The other interesting thing from the paper is they looked at the dipropyl disulfide. In some of the sampling methods, it would actually break down due to contact with the container wall. In some of the sorbent materials, it would also break down as well. So an interesting one here to keep an eye on as far as collection of CO2 and purity of CO2. So the second paper that we want to take a look at utilized actually one of our newer coatings. It's a coating called Silcolloy 2000. So we've had Silcolloy for quite some time. Silcolloy 2000 is a coating that we designed specifically for its high temperature stability. So where Silcolloy 1000 may break down at some higher temperatures, Silcolloy 2000 can often survive. And this was a paper that was done largely out of the University of Illinois at Urbana-Champaign. And we plan to actually reach out to these guys and interview them about this, because this is a really interesting paper of what they were doing and what they were looking at. So what they were interested in was new ways that you can design tubing to go into jet fighters or jet planes. If you weren't aware of this, whenever NASA and also some of the military design planes and some of our aerospace designs, weight is always something that they're concerned with. So you want to pack as much material and as many things onto those jets and rockets as you can without as much weight as possible. So one thing is that due to the combustion near the jet engines and things like that, a lot of items on the jets get very, very hot. And so there needs to be some way to cool those. Well, utilizing a coolant itself is just going to add weight. So one thing that they used or designed was using fuel as a coolant source. So the fuel actually cools a lot of the systems. But one of the issues with that is that jet fuel, as you would imagine, isn't designed to be hot and maintain stability there. Sometimes it will break down, especially it'll break down catalytically with the walls of the tubes that it is actually being held in the heat exchangers. And so here is just an image of a pre-test of a copper tube. So copper has really, really nice thermal properties. It's able to exchange heat very efficiently. However, it's very catalytic. So you can see as jet fuel A, which is what they were looking at, was introduced to a copper tube at 215 degrees C. You can see before the test, it's that nice coppery color there on the top. But underneath, after they flow this jet fuel A through at 215 degrees C, it becomes black. And under SEM and using fib cuts, they were able to take a look at the thickness of that carbonaceous material that gets deposited onto the surface of the copper tube. So copper's not great as far as carbon deposits are concerned. It will deposit a lot of carbon relatively quickly. You can see on the right-hand side here is basically the chart showing copper really off the charts compared to some of the other alloys that they tested. They looked at stainless steel, they looked at aluminum, they looked at titanium, and they looked at Inconel, as these are all materials with really nice strength, but also relatively low weight. And as you can see, aluminum performed the best in this particular study, but these are all just normal tubes that are welded and drawn into the tube formation. What they were interested in looking at was additive manufacturing of tube materials. So if you can actually 3D print the tubes out of these various materials, it gets rid of a lot of restrictions that you might have when using just normal tube material. So a lot of the benefits of additive manufacturing is things like you can just print complex geometries. There's very minimal waste, minimum material constraints. You can 3D print nearly anything these days. Uh, they're relatively lightweight compared to the tube because you can 3D print it to be exactly the way that you want it to be. And it also has the nice high strength to weight ratio as you would expect with tubing material. One of the big problems, however, is when you 3D print these various materials into these tube shapes, is they have a really, really high surface roughness. So you can see on the right-hand side, just the 316 stainless steel, aluminum, titanium, Inconel. Every single 3D printed tube has a higher surface roughness. Now, why is that important? Well, as you have more surface roughness, you're going to have more interaction with the jet fuel that's going through, and you potentially may have more deposits that occur. And sure enough, here looking at these 3 different tube materials, you can see whenever they did the 3D printed tube and they did the exact same study with 215 degrees C, sending the jet fuel through the tubes and seeing what deposits on the other end. If you look at the thickness of the carbon deposits, every single additively manufactured tube is worse than the typical standard tube material that you would just buy out of the package. Titanium was dramatically worse, aluminum very much worse as well. Inconel was the closest to the drawn material, but they were all just worse as far as the thickness of the carbon deposit that occurred on them. So that's where SilcoTek 2000 really came in to help out. So on the left-hand side here, these are all the tubes that are coated with SilcoTek 2000. You can see the nice pretty colors on the Inconel and the aluminum. Sometimes our coated tubing isn't that pretty. Sometimes it has this gold color you can see on the stainless steel. Sometimes it almost looks like it's uncoated if it's just the right thickness, like you can see on titanium. But as a result of coating these tubes, you can see in the middle graph here, every single one of those additively manufactured tubes had thinner deposition thicknesses of the carbon deposits after exposure to the jet fuel. And interestingly enough, clear on the right-hand side, rather than just looking at how thick the deposits were, they actually looked at the weight percent of carbon on the surface of these materials. And you can see essentially what we're looking at is we really want to compare the dark red with the dark green and the medium green. So the dark red there is the tested tube materials, just standard tubes with the jet fuel run through them. The medium green with the slashes going from upper left to lower right, that was the additively manufactured tube material that was tested with the jet fuel. And the green material, or the green bar there, is the SilcoTek coated additively manufactured tubing. And this is interesting for 3 reasons. One is every single one of those additively manufactured tubes saw less carbon buildup on it with the coating, so that's great. The second interesting thing here is you'll notice where you see the variation from stainless steel to titanium to aluminum to Inconel with the pure tube versus the variability with the additively manufactured tube. You can see in that dark green straight across, they all had relatively the same amount of weight that was deposited on the surface of those tubes. So it really brought in some consistency for their measurements. And then finally, you can see how it didn't quite get it down to the same level of carbon buildup on all of them. But if you'll notice for aluminum, as well as for Inconel and titanium, the additively manufactured tube with the coating on it actually produced less carbon than the standard tube itself. And I'd be really interested to see what these would look like if the standard tubes were coated with SilcoTek. I believe they may have done that. I'll have to look a little bit harder. However, this was a really nice paper showing just how beneficial having inert surfaces, especially to stop catalytic breakdown like the jet fuel touching these tube walls, can do for you and do for a variety of other applications. So with that, like I said, this is our first try at this. Be on the lookout for us in the future with publishing these videos. If you have any questions in the meantime, feel free to email us at service@silcotek.com. You can call us at the phone number shown below, or if you're in the area in central Pennsylvania and you want to stop by, let us know, and we'd be happy to have you come and visit. So until next time, this is Jesse Bischof, a senior scientist here at SilcoTek, signing off, and we'll see you for the next episode of SilcoTalk.